Hi everyone, and welcome to our video on more on Lewis structures and Vesper shapes. Hopefully this is all review from Gen Chem, but just to make sure there's no gaps or if you find we've missed something, we'll have this video so you can always come back later and check and make sure you've got everything. So the first thing we're going to talk about, we sort of went through the basic rules, so I'm just going to show some different examples and some different things that we didn't have time to talk about probably in class. All right, so the first thing that we're going to look at is this example, and we're going to go through the strategy just like we did in class. So we're going to do NH2F. So the first thing we're going to do is look for the number of valence electrons where it says number 1. So if we look at that, we're going to use the periodic table. So nitrogen has how many valence electrons? Right, it has 5, hydrogen has 1, and fluorine has 7. So we'd add those up down here. So when we add those up, we're going to get 14 electrons. Remember I said I like to divide them by 2 just so I can draw them by pairs. So I'm going to do that. All right, so we got 7 pairs. So now the next thing we're going to do is pick the central atom. Now we said the central atom is going to be the least electronegative. So out of these 3, hydrogen's actually the least electronegative, but that's an exception, so it can't be in the middle. So it's going to be nitrogen. So we're going to pick nitrogen, and then we're going to connect the other atoms around the nitrogen. The next thing we're going to do is add the remaining electrons from number 1, so that's 7 pairs, around the central atom and around the other atoms until we have all the electrons. We're going to do that using the octet rule, so we want things to have groups of 8 where they can. So let's look at what that looks like. Remember I said that I like to do my lone pairs like a line like this, but you can also do your lone pairs as dots. I like to do lines because it saves time, and also if you're looking from far away, I'm used to drawing on a board, and it's hard to see the dots sometimes. So this way I know everyone can see what I'm drawing. So then the last thing I'll mention is we should check the octets and we should check the number of electrons. The most common mistakes are people either not doing the octets or having too many or too few electrons, and that's going to make you miss the whole problem. So you don't want to do that. So I'm going to check. I was supposed to have 7 pairs, so I have 1, 2, 3, 4, 5, 6, 7 pairs. And then does everything have an octet? So nitrogen has 2, 4, 6, 8. Fluorine has 2, 4, 6, 8. Hydrogen is an exception, so it doesn't need to have 8. It's only allowed to have 2 electrons, so that means this is a good structure. One more thing I want to mention before we move on is that I know that some people have done Lewis dot structures maybe a little differently, where you had the electrons localized. So what that would look like is if nitrogen was here, I would start with the nitrogen like this. So here I've drawn all the valence of electrons of nitrogen on the nitrogen itself as if they belong to it. Then I would add the other atoms and have only the electrons that belong to those. So like if I drew the hydrogens like this, so they're each adding 1 electron for their valence electrons, and then I would draw the fluorine over here. And so fluorine has its 7 electrons. And the thing about this is it kind of all works out in a neat way here, but it's totally unnecessary. It took a whole bunch of extra time. There's no reason to differentiate where those electrons came from. And it also becomes weird whenever you're trying to figure out what happens with a double bond. Like, did both the electrons come from the carbon? Did they both come from the oxygen? That doesn't matter. That's so slow. So instead, if I just write the electrons and fill them in with lines like this, so I've already got my connections made, and then all I have to do is just say, how many more do I have? I have 3, I need 4 more. 1, 2, 3, 4. That's a lot easier, quicker, and it's going to work a lot better in the long run, and it's easier to see what you've got. So there's a basic one, but then what happens if we have charges? We may or may not have made it to that spot in class. So let's take a look. So here's 2 more examples. We're going to do CO3 2 minus and H3O plus. So that way we can have a plus and a minus. The only thing that's going to change for these 2 examples is going to happen in step 1, where you count the valence electrons. So valence electrons are negative, so that's going to affect our math. So if we look here, we've got CO3 minus 2, and that means we're going to have 4 for carbon, we're going to have 6 for each oxygen, and then we're going to add 2 electrons. Because electrons are negative, if the overall charge is negative, that means you have more or extra electrons. So we're going to add. Now, if we do the same thing for example 3, we'll do the same process for step 1. So there's 3 hydrogens, so 3 times 1, because each one is 1 valence. And then oxygen has 6, and we have a positive charge. So what do we need to do to the electrons? Right, we need to have actually 1 less electron in this case. So we're actually going to subtract 1, and that's going to give us an overall positive charge. So then that's going to equal 8. So then I'll do the same thing. I'll add up the totals. And then as you can see over here, I've got 24. I'm going to divide that by 2 to get 12 pairs. Then I'll do the same thing over here. I've got 8, so I'll divide that by 2 and get 4 pairs. So then we can go through the rest of the process, but it's just going to be the same for the Lewis dot structures. So for example 2, whenever I do the central atom, I'm going to choose carbon and connect everything around that. And whenever I do example 3, I'm going to choose oxygen because hydrogen's not allowed to be in the middle. So that's going to be the central atom, and I'll connect all the hydrogens around that. And then I'm going to add all the electrons using the octet rule. Again, I'm using the total that I got from step 1. So for carbon, I would put them all around here. And then if I put them all around like this, as you can see, whenever I check the octets, one of these doesn't have an octet. So what's the problem there? Right, the carbon doesn't have an octet. So then I would take the one from the outside of oxygen, move it to make a double bond so that way they can share. The reason I always add the electrons on the outside is because I can do that if I need to. If you add them all in the middle, then you always end up like erasing or scratching out, and it's always harder. So I like to start on the outside and move in, then it's a little bit more obvious when I need to make a double or triple bond. All right, so then if I do the same thing with the H3O+, that's a lot easier, right? I just have to add 2 more electrons because I've already got 6. So I'm going to add those 2 electrons there, and I'm done. The very last step again would be to double check and make sure that everything that should have octets does and that you have the right number of electrons. So if I look at example 2, I should have an octet around oxygen, oxygen, and oxygen. They each have 8 electrons, that's right. Then the carbon should have 2, 4, 6, 8 around the bonds in the middle, so that also has 8. So that one's perfect. The same thing with oxygen, it should have 8, so it has 2 on the top and then 3 bonds, so that would be 8. The hydrogens only have to have 1 bond, they're only allowed to have 2 electrons. So that's fine. Then I double check my total, so then the total for example 2 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs, and then on example 3 it should only be 4 pairs, 1, 2, 3, 4. So everything looks great, that's a good example. So one thing we haven't talked about yet is that there are exceptions to the octet rule. I mentioned it briefly in class probably, but I didn't actually go over it. So the exceptions to the octet rule are things that don't have to have or can't have an octet. So the most common exception we've already seen is hydrogen. It's only allowed to have 2 electrons. For the other ones, there's usually options. So beryllium, it can have 4 electrons and that's okay. For boron and aluminum, it can have 6 electrons, and that's okay. And for any element in rows 3 through 7, it's okay for it to have more than 8 electrons, so it can exceed the octet rule. Anything below that in rows 1 and 2 cannot do that. So obviously carbon, nitrogen, oxygen, those are never going to be more than 8 in the middle. But phosphorus, sulfur, those can have more than 8, and that's okay. Not required, but okay. So just to be sure we're clear, let's look at 2 examples. We've got example 4, AlCl3, and example 5, AlCl4 minus. So I'm just going to draw the Lewis structures. So as you can see here, example 4, aluminum only has 6 electrons around it, and that's totally fine. I don't need to make a double bond in this example because it's one of the exceptions. For example 5, I've got all 4 bonds around the middle and it has 8 electrons. That's also fine. It's still a normal molecule. Obviously, I wouldn't make multiple bonds in this case, and I have to have at least 8 electrons because I've got 4 bonds. So both of these are the correct Lewis dot structures. So let's do one more example with an exception just so we can try it out. Let's look at PO4 minus 3 charge. So this is a phosphate ion. Let's see what kind of electron dot structures we can come up with. So if we add up the total electrons, we're going to get 32. So that's 16 pairs of electrons. You can do the math yourself. Check it out. Remember, you're adding 3 extra electrons for the minus 3 charge. But then we're going to basically pick our central atom. So our central atom in this case would be phosphorus. And then we're going to put the oxygens around it like this. And then we can add our 16 electrons. So if you see, there's a couple ways we could do this. The first way is we can just make everything have an octet. So that would be a structure that looks like this. The other thing that we can do is we can actually move one of these pairs of electrons from the outside of the oxygen in and make a different structure. So that structure would look like this. So if you look at these, the only difference between these two is the placement of 1 pair of electrons. Here it's on the outside of the oxygen, and then on the right structure it's in the double bond. So the question is, which one of these is better? They're both obviously okay. We know that we can have more than an octet, so the one on the right is fine, the one on the left is fine. So how do we know which one's better? So in this case, we're gonna talk about that more on Wednesday. But basically, the answer is going to be the formal charge because they both have all octet. We're going to look at the formal charge, and it actually turns out that according to the formal charge, the structure on the right is the more correct structure. So that's the one that I would want you to put on a test. If you didn't already know that, that's totally fine. We're going to talk more about it on Wednesday. So stay tuned. We're going to get there. So with that, we're probably done with this video. We're not totally done for the day though, so don't stop yet. We've talked about Lewis dot structures in more detail, but we still want to know a little bit more about Vesper shapes and how to figure out the Vesper shape and angle based on the Lewis dot structure. So if this is fall 2020, we should be going on to the next video, which will be about Vesper shapes and that kind of thing. If it's not, then you can always check online and make sure that that's the next video for today. Thank you.